So I added a few more openings, as you can see. Again, that's primarily to reduce the overall mass of the object. The less material we use for solid blocking, the more our material will be able to be stretched. Mom is still where mom is. I added a little hole for a heart and added a little hole for a cylinder at the top. But I think the coolest thing that I've added is this guy right here. Watch this. The lettering, there you go. To mom, from you. All right, so the technique of adding letters to go onto the side is the same technique as what was done to apply the lettering for the engraving that happened here. You pull the letters out, however you are going to spell whatever your message is to your loved one for whatever object you choose to print, and then you group them, and then you size it so that it will fit on your object at some point, some way or fashion, and then you can rotate this. And so let me just do something. Let's not work with this guy. Let's just do something here and new design, because I don't want to mess that one up. So we'll go ahead and do a new design. So here, bring one in and something here like so, so that when we look at it, we can see that it is this. I'm going to get, say, 40 also, okay? All right, and let's say I want to attach lettering that's on the side of this. And so I'm going to come up to my text letters, and let's do C, and let's do A, and let's do T, cats. And let's see, there's some more here. Is there an ampersand? Oh, there is an ampersand, yes, yay, cats. And go back to first, and let's do D. And O, and G, and S. Cool. All right, so now we have cats and dogs. Now let's look at this from this perspective. We see all of our letters are all over the place. So now you can play with some spacing, use your grids. Here we go for spacing. That's good there. Let me put, come on, cat, dog, ampersand. Here we go. And let's move D over here, and O, and G, and S. Okay, so now we have a bunch of letters. I'm going to select them as a group, and I'm going to group them. And as a group, if I've grouped them properly, they'll turn one color. And from this perspective, I can change the shape and the aspect of what I want them to look like. Now, they happen to be, from this perspective, as you can see, pretty flat. I have several ways of rotating this. I can grab this particular one here. Come here. And like that. Okay. And I can move it up like this. Bring this block over into this. Let's look at it from the side. So I can move this, oops, too far forward this way. And let's look at it from this perspective. Okay, that's some nice raised lettering. And if I'm happy with that raised lettering, I can select that and hit group. And in hitting group, use a different color so it's easier to see. Now I happen to have an object that is dimensional, that has lettering on it, that is raised and delivers a very distinct message. And so this is another way that you can customize your object, whatever your object happens to be. So that's how I was able to put the lettering on my cell phone holder. So you're tasked with Tinkercad design number 3 for this weekend. And the sooner you can get that sent to Nabil, sooner he can print that out. And it should be a very, very nice gift for your family members. Say, yes, I created this in my electronics class on the 3D printer. It's my design. You can have a lot of fun with it, and I hope you do. Any questions about this particular project for Tinkercad number 3? Got a pretty good handle on the concept, the idea? Okay, ready to jump at it and create something fun and interesting for all of us to admire? I look forward to it. Okay, let's go ahead and stop the share on this particular guy and come back to here. Now, on our final review, I got a couple of things for us to play with. So I need this here, and let me go and do this. And let me share this screen with you. Okay, everybody can see my week 15 review for final screen. Okay, let me move our gallery view off the screen, get my pen ready. All right, I'm gonna give you a circuit to think about. Get your calculators ready, copy the circuit down, fold this guy up, do this guy here. Okay, insert draw. Okay, that'll work. So suppose you see, let me use a little thicker for the draw. Okay. Suppose you were to see this and I were to put a point here, a point here, point here, point here, point here, point here. And let's say we label this guy this way. Okay, so VS1 equals 10 volts. Let me make this a little larger so you can see this better, all right? So VS1 is equal to 10 volts. And let's say this is VS, I'd like to write this in a different area. Let's write this over here. VS2 is equal to 15 volts. And I have VS3 is equal to 3 volts. And I'm going to label these points right here. This will be labeled as point A, point B, point C, D, E, and F. And let's go ahead and label some of these resistors. So how about we do this? Let's make this my R1 is equal to 15 ohms. Let's make my R2 over here is equal to 20 ohms. And let's make my R3 equal to, let's make this 30 ohms. All right, I think we have all the elements. So based on this schematic and 3 resistors, 3 voltage sources, you would be asked to analyze this, think this through, for filling in the following information. You would be asked to fill in for here, 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 and here. Since there's only 3 resistors, there's an R1, there's an R2, R3 totals. there will be a V column, an I column, and an R column. And something like that. I don't like that one. It's a little crooked. Let's go ahead and do this one this way. Okay. Where do you recommend that we start this particular exercise? Oh, in addition to that, there's more. We would be looking for, and I need to give you a ground. I'm going to put a ground right here, like so. And I would be interested in what happens at VA. What would be happening at VE. And then what would be happening from V, let's say C to F. All right. Let's noodle on this, and I'm open to suggestions from the gallery. Where would we start with something like this? Is this a super outrageous superposition exercise? Do I have to do short out two voltage sources and solve for one and all of that? Or what approach would we do with this? Does it look impossible? It's not intended to look impossible, but it's certainly something you haven't seen before.
It seems like shorting out V2 and V3 would be easiest.
So would we use the superposition approach on this?
I think so.
That's a thought. Okay. And anybody else? Yusef, what do you think?
I don't know. I was looking for currents. I don't know.
Okay, Wei Ji, what do you think?
So we just make sure all the voltage sources, the polarity, and then we just add them or subtract them together to get the total voltages.
Oh, really? So let's mark polarities. I think that's a good place to start. Maybe that'll help us out. Maybe that might be revealing. So let's go ahead. This side of VS2 is negative. This side of VS2 is positive. This side of VS1 is negative. This side of VS1 is positive. This side of VS3 is negative. This side is positive. So we've now marked those polarities. So how does that help us out with the polarities? Is Weiji, you suggested something about subtracting and adding?
So VS2 and VS3 is the same polarity, so we add them together, but the VS1 is the different way, so we subtract them.
Okay. So I ask you to remember this. Remember, series aiding, oops, spell it correctly, Co. So series aiding versus series opposing. Series aiding versus series opposing. First of all, do I have a series circuit? The answer is yes. And unlike superposition, see, we use superposition with multiple voltage sources when we don't have things in series. When we have things in series, we have a simpler solution. So if you look at VS2, VS2 wants to move electrons in that direction, away from the negative, yes? So VS2 wants to move the electrons in that direction. VS1 wants to move electrons in this direction. So VS2, if VS2 were by itself and it was allowed to go around, what direction would we call the electron flow from VS number 2? That would be clockwise or counterclockwise for VS2?
Counterclockwise.
Okay, let's go ahead and put down CCW for counterclockwise, whereas VS1 would be CW for clockwise, and then VS3 wants to move, VS3 wants to move electrons in this direction, so that would be counterclockwise. Yes? So when you're facing remembering series aiding versus series opposing, what it is that you want to do is just create a simple chart of CW in one direction and CCW in the other direction. How many sources want to move counterclockwise? Well, VS2 has 15 volts, yes? And VS3 is counterclockwise and it has 3 volts. And VS1 is clockwise and it only has 10. So if you go to add these guys up, I've got 10 volts on this side and I've got 18 volts on this side. Which one is going to win? The counterclockwise wins by 8 volts. So your total voltage here would be stated as 8 volts. Let me make that just a tad larger for here. That would be 8 volts. Does everybody understand why VST? So VST is equal to 18 volts minus 10 volts is equal to 8 volts. Is everybody okay with how EST was reconciled? This is, I have 2 components in series aiding, and I've got 1 component series opposing. So the bigger total will subtract the smaller total. In this case, 18 subtracts 10, I have 8 volts. Okay, so far so good. So now that I know I have 8 volts, do I also have a final direction of current? The final direction of current is here. CCW equals final direction of electron flow. So if CCW is the final direction, does that allow me to draw my arrows flowing current through this circuit? So for example, R1. Here's R1, upper right-hand corner. The current that flows through this has to move in a counterclockwise direction, which means it must move from here to here. Is that correct? How many people agree? Raise your hands. Okay. So if it flows in this direction, and we are talking about electron flow, what polarity is on the right-hand side? What polarity is on the right-hand side of R1? Wei Ji?
Negative.
It would be negative. What polarity is on the, I'm sorry, it would on the, I keep pointing, the right-hand side is negative and the left-hand side is positive, yes? Because the electrons must flow from negative to positive. And then through R2, the current flows down, which means, so Yusuf, the top of R2 is what polarity?
Negative.
Negative, correct. And the bottom of R2 is?
Positive.
Positive, done deal. Okay. Then the current will flow through R3 in this direction, which means, Jacqueline, the polarity on the left side of R3 is what polarity?
Negative.
Would be negative, correct. And then the right-hand side would be positive, yes? Okay. Everybody okay with the polarities on each of the resistors? That's critical. All right. Now, that being said, we have fundamentally a series circuit. So can we fill in our known values? Let's go ahead and do that. We have R1, which is 15 ohms. 15 ohms. We have R2, which is 20 ohms. You have R3, which is 30 ohms. And if they're in series, what's my total ohms?
65.
Like 65 ohms, yes? 65 ohms. All right. And we agree we have an 8-volt source. Guess what I'm going to ask you to calculate next? What do you think?
Current.
Now let's go ahead and find that current. So 8 volts divided by 65 ohms. So that question goes to Jacqueline. What do you calculate for current, dear?
123.08 milliamps.
123.08 milliamps. Are we all in agreement with that value? Now, since the RT is your first calculation, you want to make sure your RT is added correctly. What happens if you start off with an incorrect RT? What happens to almost everything else in your analysis? It goes sideways, right? So you want to make sure your RT, you're confident that is 65 ohms. Then you just calculated current, and you know with the series current, we would normally fill this column entirely in. But before you do, what's the prudent thing to do, especially for a final exam, is recalculate, yes? So let's go ahead, take a moment, clear the calculator, take 8 and divide by 65 and confirm that number. And yes, are we happy 123.08? And if you are, then let's go ahead and fill that in. 123.08 milliamps, 123.08 milliamps, and 123.08 milliamps. Woohoo, there we go. Now it's just a matter of academics to fill in the voltages, yeah? So what I'm going to do is I'm going to ask for, let's see, Wei for R1, Jacqueline for voltage across R2, and Yusuf, the voltage across R3. So let's go ahead and do that. So Jacqueline, do you happen to have the voltage across R1, please?
I was voltage across R2.
R1 is 1.85 volts.
Well, thank you, Wei. So Wei, you have 1 point what?
1.85 volts.
1.85 volts. Very good. And Jacqueline for R2?
2.46 volts.
And we have 2.46 volts. And Yusuf, what do we have for the voltage across R3?
3.69 volts.
3.69 volts. Okay. And what would be the prudent thing to do after calculating all these voltages?
Recalculate.
Or add them up. You can also do that because you know if you add them up, the individual VR1 plus VR2 plus VR3, what should those three add up to be equal to?
8.
Equal to our voltage source, yes? And if you go to add these guys up, yes, they do add up to be 8 volts, and yes, that has been double checked. You can recalculate, that would be fine, each one of those separately, or you can add them up. This plus this is equal to the 8.8 volts. So far, so good. Now comes the interesting part of our analysis, and this is kind of leading us into your take-home test number 3, is finding voltages at specific points and finding voltages between 2 points. So take a look at the very first one that's being asked of you. The very first one that's being asked of you is VA. We'll find point A. So point A is right here, and the voltage at A is from that point. You put the red probe there. Where are you going to put the black probe? How do you measure voltage if only one point is given?
The black probe to the ground.
Black probe will go to ground. Are we in agreement with that, everybody? So the black probe will go to ground, red probe will go to point A. They are diagonally opposite each other in this schematic. Wow. So how do I reconcile the voltage at point A? Well, this is what we would do. This is what we would do. I would go ahead and do this. Okay, green is fine. So I would go from point A all the way around to ground this direction, okay? And as I do, I'm going to count voltages along the way. So take a look at point A. I'm going to move to the right. From point A, as I move to the right, I see a polarity. What polarity do I see here? Negative. And how much voltage is the source? 15. So VA is equal to a negative 15 volts. and we're going to add it to something. The next thing we encounter, once we go past this voltage source at point B, we see what polarity right here? Positive. And how much voltage is on VR1? What is my voltage on VR1 according to here?
1.85 volt.
1.85. So I'm going to add a 1.85 volts right there. And I'm going to add more. Now I'm at point C. Now at point C, I still have one more component to reconcile before I hit ground. And so from point C moving down, what polarity does the red probe see right here? Negative.
Negative.
Negative how many volts? 3 volts. So I'm going to add a negative 3 volts. So take a look at what we're adding together here, my friends. VA is equal to the sum total of these three values, negative 15 right here, or positive 1.85, and a negative 3 volts. When you go to add all this up, it becomes, clear, turn on the calculator code, that helps. 1.85. All right, who's got a number for me? Jacqueline, you got a number for me? I didn't hear that, I'm sorry.
Negative 16.18 volts.
Negative 16.18 volts. How many people concur?
It's not point
Everybody
15.
agree?
15.
15. Perhaps I heard wrong. I'm sorry. It does work out to be 15. There we go. Negative 16.15 volts. Everybody okay with that?
Yeah.
All right. Now, suppose, was there a question? Okay, I don't want to miss a question. Now, suppose we didn't take the green path across the top of the circuit to go to ground. Suppose we take a different color path. Suppose I took from VA, the blue path, and went this way to ground. I'm still going from A to ground. So if I'm starting at point A and I follow the blue path, what polarity do I see here first coming down from point A? I see a negative, yes? And what is my voltage on VR2? It would be a 2.46. So I encounter a, oops, come back here. Come back. I encounter a equals, well, from here equals a negative 2.46 volts. And I'm going to add it to something. So as I come down from A, I encounter the negative 2.46. I'm now at point F. At point F, if I move towards the right, I encounter what polarity right here? A negative, and this source is 10. So plus negative 10 volts. And then, lastly, I'm at point E. I've got one more to reconcile before going to ground. Again, what polarity does the red probe see first? Negative. And how much voltage is across R3? 3.69. So I'm going to add a negative 3.69 volts. Negative 3.69 volts. So if I go to add these all together, what do I end up with? I end up with a negative 16.15 volts also, which is what I should end up with. I shouldn't end up with anything more. I shouldn't end up with anything less. So is everybody okay with either path from A to ground, whether we take the green path going over the top, down the right, or whether we take the blue path going down the left and over to the right? Whichever path we take, algebraically, they should be the same number, same polarity, same number. All right, good. How about the voltage at E to ground? What do you think? E is right here, and ground is right here. Yusuf, what do you think? If my red probe's on E, and I'm headed towards ground, the first polarity I see is a what?
Yeah, negative.
And then as
Negative
it's negative.
3.69 volts.
And would that be all there is? That's an interview question.
I
That
guess
is
so.
all there is.
Yes.
Yes, that's an interview question. Yes, you want to answer that question assertively and say, yes, of course, there's nothing else. It's got to be 3.69 volts. That's the shortest path between 2 points, and it's a negative 3.69 volts. You could interject at this point and show how smart you are to your interviewer and say, well, if we went the long way around and walk this through with me from point E to F, point F to A, point A to B, point B to C, and finally from C down to ground. If you algebraically added 1, 2, 3, 4, 5 different voltages, guess where you'd end up? Negative 3.69 volts, if your numbers were correct. Okay. Any questions on VE to ground? Okay, Wei Ji, how do I do this last one, CF?
So we start with the C point, and then we go. Either way you want to go is fine.
So VCF. So I start with my red probe on C, and I want to go to F. Does it matter which way I go? Down first and then to the left, or left first and then down?
It doesn't matter.
Does not matter. Good. Give me one path. Give me some numbers. Which path do you want?
We go down first.
Okay, let's go down first. Okay, so C coming down, what's the very first thing I'm going to add?
Negative 3 volts.
Negative 3 volts. Done. What am I going to add that to?
A positive 3.69 volts.
Positive 3.69 volts. And what am I going to add that to?
Positive 10 volts.
Plus a positive 10 volts. 0, 0.
That will be it.
Okay. And let's see what that works out to be. Negative 3.
10.69.
Positive or negative?
Positive.
Okay, so we say it should be a positive 10.69 volts. Suppose we went the other direction. Suppose we went across the top first. What would those numbers look like?
Negative
C to D.
1.85 volts.
We would have a negative 1.85 volts. What are we adding that to?
A positive 15 volts.
Positive 15 volts. Right there. And what are we adding that to?
Negative 2.46 volts.
Negative 2.46 volts. Right there. And so if you go to add all this up, what does this reconcile to be?
10.69 volts.
Positive 10.69 volts also. Is everybody okay with all the math pertaining to this exercise? So this is a good reminder that you only use superposition for series parallel multiple voltage sources. Here, since everything is simple series, we don't have to use superposition. It simplifies to be nothing more than series aiding versus series opposing. Okay? All right. Let's move on to another exercise. And the next exercise will be this. Let me scoosh this guy up. And the next one. Okay. I'm going to draw a circuit for you. And let's say this guy works out to be here. and here. And I have an R1. Oh, before I do that, let me just go ahead and finish this up. Let's do a voltage source here. And now I'll go ahead and label everything. And the labeling will look like this. So my voltage source, Vs, will be equal to 65 volts. And here's my R1, here's my R2, here's my R3, here's my R4. And my RL1, my RL2, and my RL3. The data that is required for this is, let's see, before I finish that up, go ahead and put this in. That's point A, B, C, and D. Let's go ahead and use some different colors here, make it more distinguishable. So A, B, oops, sorry, B is over here. And this one is C, and this one's D. So this is our circuit as it looks right now. And the other parameters are RL1 is going to be 46 volts, comma, 15 milliamps. This one is going to be 27 volts, comma, 30 milliamps. This one's going to require 14 volts, comma, 6 milliamps. So those are your beginning parameters. And as we have 3 load resistors and 4 string resistors, you're going to have 8 rows to be able to put together. All right, so 8 rows. While you're copying that, let me take this call. Hello, how can I help you? Thank you. All right, we're just trying to get things ready for my students this evening. Let's see here. Okay, so you're going to be asked to do a VIR analysis for all of these components. What will that look like? It'll look something like this. So here, 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 that's VR 1, 2, 3, 4, and then load resistor, another load resistor, another load resistor, and finally totals. Okay, a few things. R1, R2, R3, R4, RL1, RL2, RL3, and totals. Oh, that's a horrible line. Let's see if I can do this a little better. Okay, so we happen to have V, I, and R. Wow, all right, 8 rows, 3 columns, that's 24. Looks very, very similar to take-home test number 4. So if each one was worth 4 points, you're looking at like 96 points total on this exercise. So how are we going to earn, plus you get, what's that, what do we say, 96 points? Okay, 4 points for your signature. So it's a 100-point exercise. Where do we start with something like this? Who's got a suggestion?
Find the bleeder current.
Okay, bleeder current. All right, yeah, I like that. And what was the rule for my bleeder current? First of all, maybe we should define the bleeder resistor. Bleeder resistor is equal to which resistor? Jacqueline?
Are you asking for the law or the specific resistor for the circuit?
No, just the specific resistor.
Okay, R4.
R4. And we define R4 as the bleeder resistor because it is the last of the string resistors. String is a nickname for series. So this is a voltage divider, loaded voltage divider network. So we have 4 resistors that form the string that branch off to service the needs of different loads. And so the string resistors are R1, 2, 3, 4. And R4 is the last of the string resistors that's finally connected to ground, and it is attached to the last load to ground. So it is indeed R4. Once we identify the bleeder resistor as R4, then you need to determine the bleeder current. So the bleeder current is a capital I with a little b, BL, bleeder, if you will. And that's determined as 10% of the total load current. Is that right? All right. So we need to determine some load currents. And we can probably go ahead and fill in the chart with respect to the load currents and load information, yes? So why don't we go ahead and fill in some things? We have 65 volts as the total voltage. We have voltage that load 1 requires, that's 46 volts. We have the voltage that load 2 requires is 27 volts. You have the voltage that load 3 requires is 14 volts. You are also given the currents. So load 1 demands 15 milliamps in order for it to work. Load 2 is 30 milliamps in order for it to work. Load 3 is 6 milliamps in order for that to work. And if I add all 3 load currents together, what am I going to get? It looks like 15 plus 30 makes 45 plus 6, 51 milliamps. Does that look right to you all? Okay. So I have 51 milliamps is the total load current. And we said that the bleeder would be 1/10 of total load current, which is equal to 51 milliamp divided by 10. So that's equal to 5.1 milliamps. Is everybody okay with that? 5.1. Where in the chart does 5.1 milliamps go?
Current for
R4,
R4.
R4.
Current for R4. Does that make sense? Is that all right? So I have 5.1 milliamps for R4. Very cool. Now that I have this current, what method do I use to solve for this exercise? I have 5 milliamps identified right here.
5.1.
What is the name of the method? So we are going to use current analysis, or you could use voltage analysis. We're going to do both. So with current analysis, let's go ahead and polarize everything that is happening with respect to this schematic. The top of my source is polarity.
Negative.
Negative, because I have the short plate on top. Long plate is here. All right. And which means that this side of R1, the left side of R1 is what polarity, everybody?
Negative.
Negative here, and this side would be?
Positive.
Positive right there. Okay. And then the top of R2 would be, oops, come back here, too fast. Oh, I took away the whole resistor. Only me. Okay. So we have, this is going to be negative, this is going to be positive, this is going to be negative, this is going to be positive, this is going to be negative, and this is going to be positive. Yes? So far, so good. Which way do the electrons flow in this particular case? electrons will leave the negative plate of the voltage source. So let me expand this. The electrons will go up and go to the right. And once it hits this node, what will happen at this node, at node B? The current will split. Part of the current will go here, part of the current will come down, yes? Of the current that comes down from point B through, oops, come back here, from point B through R2 to ground, once this current hits node C, what happens here? It splits again. Part of it goes that way, part of it goes this way. Once the current comes through R3 to node D, it splits again. Part of it goes there, and part of it goes here. And what happens to the current that hits ground? The current that hits ground comes back up to the positive side of the source. So do we have complete paths for current to flow? The answer is yes. Now, how do I reconcile my currents? Well, take a look. I got 15 milliamps flowing down from node D. Do I know the current that is going to the right through load number 3? I know that there's 6 milliamps here, yes? So if I have 5 milliamps flowing down from the split, 6 milliamps flowing away from the split, how much current must be coming into that split in order to split off 6 and 5 milliamps?
11.1 milliamps.
Okay, so this works out to be 11. And if you use all your decimal places, does it work out to be the 0.1? It looks like 11 milliamps. I'll leave it as 11 milliamps for now, but you could very well be right if we did all of the...
Because the bleed...
What's 10% of 51?
Oh, 5.1. I miswrote something. Yes, you got to catch me here. Yeah, this should have been 5.1 milliamps. 5.1 milliamps. There we go. Now we're happy with 11.1 milliamps right there. Okay, good. Is everybody all right with that math? 11.1 milliamps has to flow down through R3 in order to split 6 to the right and 5.1 milliamps flowing down. Now, at point C, we have a split. The current that flows to RL2 is 30 milliamps. So I have 30 milliamps that flows in this direction and 11.1 flowing down. What must come into node C in order for me to split this way?
41.1.
Add these up and it should be, yes, 41.1 milliamps. Is everybody okay with that math so far? And the current that feeds RL1 was given as 15 milliamps. So I have 15 milliamps flowing away from point B. I have 41.1 milliamps flowing away from point B. So what is my current through R1? My current through R1 is the sum of those that split. So that works out to be 50 what?
6.1.
56.1 milliamps. Is everybody okay with how the current analysis, how the current analysis is done? So far, so good? All right, let's go ahead and take a look at voltage analysis. Voltage analysis is equally valid. And voltage analysis, look at this. Do we have a load requirement of 14 volts for RL3 to ground? That means the voltage at point D, which feeds this 14 volts, the voltage at point D must be 14 volts. Is that also the voltage we call VR4? The voltage at point D is parallel between the load to ground and R4 to ground. So you know that in parallel, the voltages are the same. So if this load requires 14 volts, then we must have 14 volts across R4. So R4, let's go ahead and write down 14 volts. Now, if we continue with voltage analysis, does the second load specify a required voltage? The second load specifies it needs 27 volts. And that is attached to point C. So that means point C, voltage at point C, must be equal to 27 volts. So if I have 27 volts on the top, if I have the 27 volts on top of R3 and 14 volts at the bottom of R3, then how much voltage is dropped between point C and point D?
13 volts.
Looks like 13 volts, yes? Would you agree? We have 13 volts. So we have 13 volts right here. Boop. And if you take a look at the top of the circuit, the first load is requiring 46 volts. That means the voltage at point B must be 46 volts right here. So VB is equal to 46 volts. So if I have 46 volts on the top of R2 and I have 27 volts on the bottom of R2, how much voltage do I have across R2?
19 volts.
Looks like, yeah, you're both right, 19 volts. Is everybody good with that so far? Do I have voltage at point B that's identified as 46 volts? What is my voltage at point A? A to ground is going to be what?
65 volts.
Okay, yeah, it's actually, all of this should be, let me change this. Make that a V. V is actually equal to negative 65 volts. Voltage at point B was a negative 46, as it turns out. And voltage at point C, all of these work out to be negative. That's fine. Voltage at point D is a negative 14. Voltage at point C is a negative 27. So VA is at negative 65. Voltage at B is negative 46. So across R1, how much voltage do we have?
Negative 19 volts.
Well, VR1 would have no magnitude. So VR1, the voltage across R1 is just simply 19 volts.
19 volts.
Yeah. Only if we measure at specific points to ground will polarity be a concern. But if we're voltages across single resistors, there's no polarities. So take a look at this. We solved this using current analysis before. We did solve this using current analysis as well as voltage analysis. So let's go ahead and fill in our current values. We discovered that we have 5.1 milliamps here. We have 11.1 milliamps here. We have 41.1 milliamps here. And we have 56.1 milliamps here. And if that's my current leaving the source, then that must be my same current coming back. It must be my total, 56.1 milliamps. Did we complete filling in the voltage and the current columns? Two different methods, but we filled in the columns. So now can we go ahead and calculate R very quickly? All right, so Yusuf, you can have R1, you can have R1, Jacqueline, R2, and Wei Ji, R3, and then we'll continue with that sequence, that order on down. So voltage divide by current. And Yusuf, what do you calculate R1 to be?
338.68 ohms.
338.68 omegas. Okay, looks good. And Jacqueline, what do you calculate your R2 to be?
462.29 ohms.
462.29 ohms, very good. And Wei Ji, what do you calculate your R3 to be?
1.17 kilo ohms.
Ohms. 1.17 kilo ohms, very good. And back to you, Yusuf, what do you calculate your R4 value to be?
2.75 kilo ohms.
2.75 kilo ohms would be correct. And Jacqueline, what do you calculate your first load resistor to be?
3.07 kilo ohms.
3.07 kilo ohms is correct. And Wei, what do you
900
calculate
ohms.
load to be? 900 ohms is correct. 900 ohms. And back to you, Yusuf. 14 divided by 6 milliamps. What do you get?
2.33 kilo ohms.
2.33 kilo ohms. And Jacqueline, wrap us up with the total.
1.16 kilo ohms.
1.16 kilo ohms. Is everybody okay with all of those calculations as they stand? 1.16 kilo ohms. Now, let's take this exercise and separate this as a series parallel exercise. So if we separate this as a series parallel exercise, let's see what this might look like. So okay, so here I happen to have a load. Here I happen to have another load. And here I happen to have yet another load. So if we had all of the values that you all had stated in our calculations, if I put in 338.68 ohms over here, and I go to put in 462.29 ohms here, 1.17 k ohms here, 2.75 k here, and then I have for RL1 3.07 k ohms here, 900 ohms here, and 2.33 k over here. How would you reconcile this circuit down to an RT? Where would you begin? If we didn't have to do voltage divider analysis, if we didn't have to calculate for voltages, didn't have to calculate for currents, where would you start with this particular exercise? My recommendation is the deepest part of the circuit, and that would pertain to my R4 and RL number 3. Okay? Because does R4 and RL3 have a unique relationship? What is their relationship?
Parallel.
They're in parallel. So if these two guys are in parallel, could that simplify to become something closer to this? Is it possible that I would have here, here, and I would still have this guy out to ground. I would still have this guy out to ground. And however, from here to ground, I will have combined these two to become this. And this would be my R4 parallel with my RL3. Is that correct? Does that part jive with our understanding so far? And if we go to put those two in parallel with each other, calculate 2.75 parallel with 2.33, if you would. 2.75 parallel with 2.33.
1.26 kilo ohms.
1.26 kilo ohms. Okay, you've taken, let's see, what did we start off with? 7 resistors, and you've now simplified this down to 6 resistors. We're on our way. Now, what would be the next thing we would do? What else can be simplified?
R3 parallel with RL2.
We have, this is my R1, this is my R2, this is my R3. And this guy goes to ground. And this is my RL1, and this is my RL2. So what did you say, Wei Ji?
R3 parallel with RL2.
How many people agree R3 is in parallel with RL2?
Yes.
Watch my head. Watch my head. What's my head doing? As you can see my head. My head is going like this.
We have to combine the R3 with the equivalent first.
Yes. You have to combine the R3 with the equivalent first. Okay, because here I have an R3 that is in series with my REQ number 1. I have to combine these guys first, then put it in parallel with RL2. So my R3 we calculated was 1.17K, yes? 1.17K. So what's 1.17K in series with 1.26?
2.43K.
So this should work out to be 2.43K ohms. So what we ought to do, keep things legitimate here, is we ought to have done this. Actually, let me go up here, and I need the space. So here, 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 dunk, 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 here, and my load resistor. This is my RL1, and then right here would be my RL2, and right here would be this guy. And this is my R3 in series with REQ number 1, and that works out to be 2.43K ohms. That, my friends, is in parallel with RL2, which you all calculated as being 900 ohms, yes? So now you can do a parallel relationship between these guys, yes? So let's go ahead and calculate that. So 2.43.
656.76. Oh.
Okay, works out to be 656.76 ohms. So this would be what we would call, let's call this REQ number 2. Is that all right? So you've now taken 7 resistors down to 6 resistors, down to, where did this come from? Go away. Down to 1, 2, 3, 4, ultimately 5 down to 4. So what does the next circuit look like? The next circuit would look like this. Let me finish this guy to ground. All right, so the next circuit would look like this. Here's my source, goes to ground, come up here. I have a resistor. I have a load resistor to ground, RL1. And then I happen to have my R1, I have my R2, and I happen to have an REQ2 that is 656.76 ohms. Is that what we have so far? Is that right? Looks reasonable. We're slowly withering this thing down, whittling this down. So what would be the next step? What would be our next combination?
We combine R2 and REQ2.
Combine these two. So here, their relationship is series. So I would have R2 plus REQ2. And R2, we determined, was 460 6229. So let's go ahead and put that in here. 462.29 ohms. So when you go to put these guys together, here, 462.29, and I'm going to add to the 656.76. What do they become?
1.12 kilo ohms.
They become 1.12 kilo ohms. So now what we're doing is we're taking the 4 resistors and we're now bringing it in this direction down to 3 resistors. And that would look like this. Here's my RL1, here's my R1, and my new resistor. Let's call this REQ3. And this is 1.12 kilo ohms. And I do have this side connected to ground. So what do I do with this? We determined a load resistor. What was the value of the load resistor? Looks like 3.07 k ohms, yes? So I'm going to put this in here, 3.07 kilo ohms. And let me double check that on our big chart. Yeah, RL1 was in fact 3.7 k ohms. So here we are. What do we do with this as our next step? Combine these two fellas that are in parallel, right? Because this would be my REQ number 3 in parallel with RL1. And let's go ahead and do that calculation. So 1.12 parallel with 3.07. Jacqueline, do you have that number for us?
820.11 ohms.
I get 62. If we're a few hundredths away from each other, that's fine. But we end up with this guy, which ultimately, one last redraw, and the last redraw we can put right over here. And we can call this REQ4, and this was 820.62 ohms. And the value of R1 we determined much earlier.
338.68 ohms.
38.68 ohms. Oops, come back here. 338.68 ohms. Do I have enough information to determine an R total?
Yep.
So it looks like my R total should be equal to R1 plus REQ4. It should be equal to the 338.68 ohms. And I'm going to add that to 820.62 ohms. So now if we go to add those up, clear, so let me 338.68 plus 820.62. Let's see if we come within a few hundredths of the previous calculation. So we say through circuit analysis and circuit reduction, we end up with 1.16 kilo ohms. Is that right? Is that what you add them up to be? 1.16 kilo ohms.
Yes.
And this value was calculated via circuit reduction and simplification. So that's how this value was arrived, 1.16 k ohms. What did we end up with on our chart? On our chart, we
Same
ended
thing.
up, wow, look at that. Are you guys feeling really good about understanding electronics analysis now? Our total was determined two totally different ways. Our total was determined at the end of 24 calculations in a VIR chart by using Ohm's law, presuming everything else was right. That's how our total was determined. Our total, on the other hand, was determined through circuit analysis and circuit reduction, starting from here. So this would have been our number one drawing. Our number two drawing would have been this guy over here, number two. Our number three drawing would have been this guy over here, number three. As we continue this, this would have been our number four drawing right there. And then we continue with drawing number five. And finally, we end up with drawing number six. So it took quite a few steps, but we end up with the same value. Another good step towards our review towards the final. Any questions on this exercise that was solved two different ways, this loaded voltage divider? Are we pretty solid, I hope? All right, well, you'll find out. I posted two take-home tests, take-home number 3 and take-home number 4. Jacqueline, you want to take a look at voltage at point B and voltage at point DB on take-home test number 3. You want to look at that a little more closely? Okay. Hopefully with this newfound knowledge, I would recommend using a red pen and using a black pen for your probes, and that might help you better visualize what your measurements on paper may calculate to be. So I'm going to stop this share, and yay, we're back to normal. Cool. Well, we got 3 minutes to spare. I think I'll spare you those 3 minutes and open it up for any questions that any of you may have regarding the work that's in front of us so far.
Will the deliverable sheet be up tonight?
I've got 2 other classes that I've got to lecture this evening. I'll try my best to give you a deliverables this evening, but if you don't see it this evening, you'll see it tomorrow morning for sure. But I have, right after you guys got 2 more classes to do. So hopefully with the Tinkercad tips that I've given you, hope that stirs your imagination for some kind of thing. And so the theme for the third one, you've already designed 2 Christmas ornaments. And you got to remind me, come Monday, I have the hooks for you guys for the Christmas ornaments. But what you want to think about for this third item is something that will sit on somebody's desk or sit on somebody's nightstand or bureau as a gift for your significant person, and not to leave the other parent out. For those of you who have 2 parents, we can design one this week and call this, what do we call this? Tinkercad design number 3. And for your other significant person the following week, our last week together, we can do that Tinkercad design number 4. So that way, neither significant adult person in the household feels left out. Is that all right? Okay, I think we'll have fun with that. Okay, my friends, with that, I will go ahead and take our picture. Yay. This is the fun part of the evening I get to do. Hey, Yusuf, lean a little closer to the camera. And I see you all. Smile. Yay. Gotcha, guys. I think. Yes, yes. All right. All right. Well, with that, have a lovely evening. Contact me through Discord if there's any questions. Take care. Have a great weekend. Bye-bye.